If the sample size, that's why we say that if you want to predict something, take care of having enough sample size, because it's the sample, and we say that like 15, similar to the logistic regression, if there is one predictor variable, at least 15 samples should be there. If there are two, then 30. And so minimum sample size should be 15 per predictor variable. So this is the one. Then I will go to the multiple linear regression. So this multiple linear regression, nothing new in this from the yesterday session. The only thing is, like, instead of one variable, you take more than one variable as a predictor variable. So the equation for this multiple linear regression would be like y, which is the dependent variable, and then beta 0, that is the intercept. And then yesterday we did like this coefficient and then this value. But again, if there are more number of predictor variable, so we explain like beta 1 x1 plus beta 2 x2 and so on, along with one error. So like here, I've just asked one question, that if I want to predict the SpO2 level of patients based on the age, gender, smoking status, fever, respiratory rate, and duration of breath hold, then what should I do? So, because there are multiple predictor variable, so I want to predict a continuous outcome, I will go with this multiple linear regression. So why we call it as a multiple? Because there are more than one predictor variable. Why it is linear? Because again, in this, we are forming a linear equation, because the value of outcome variable changes linearly with the predicted variable collectively, and regression because the equation is for the linear regression relationship. So there are some underlying assumptions, and it is almost everything is the same as you have done for the linear regression, simple linear, except that here we add one more assumption, that is the multi-collinearity, and that we'll see. So underlying assumption is one dependent variable which should be continuous. And then in this case, the independent variable can be continuous or a nominal. The errors that should be independent, they should not be autocorrelated, which we test by the Durbin-Watson statistics. Then there should be linearity in the residuals. There should be homoscedasticity. That means variance of those residuals should be similar across the fitted value of the predicted value. Then there should not be multi-collinearity. This concept we will learn, because I have not still touched this concept. And then there should not be unusual point like outlier, high leverage, or high influential point. And then the residual should be normally distributed, as we see by the PP plot and the QQ plot. So there's an important point to remember at this level, that if any variable in your independent predictor or the predictor variable is ordinal in nature, like socioeconomic scale, it is ordinal in nature. You can still put it in multiple regression, but again, that ordinal nature will be lost. Like you cannot say, you have to treat it like a nominal variable. And I hope you know by this time now what is a nominal and what is an ordinal. In nominal variable, that order does not matter, whereas in ordinal variable, that order matters. So in this case, this multiple linear regression, standard multiple linear regression, in this case, you have to treat it like a nominal variable. So the question is, I have to predict the cholesterol level based on the age, gender, BMI, and SBP. So now we have done that linear relationship between the dependent variable and the independent variables collectively. And that we test by the plotting a scatter plot of residual versus the unstandardized predicted value. And this we have seen previously. The concept of homoscedasticity, I'm just repeating these concepts. So we check for the homoscedasticity of residuals, and this is known as the equal error variances. That means it is assumed that the residuals are equal for all values of the predictor dependent variable. Again, we check this heteroscedasticity. with the same scatter plot, that is the residual versus fitted value. This independence of observation we have discussed in the previous session. And now coming to multicollinearity. So what is a multicollinearity? Basically, multicollinearity happens when there are more than one predictor variable and both are continuous in nature. So it generally occurs when we have got two or more independent variables that are highly correlated with each other. It can happen with the categorical variable also. So in that case, what will happen that you can replace one variable with the other, because then there will be problem with understanding the effect of one variable with the other. And it creates some technical issues also while interpreting the equation. So it is a situation when two or more independent variables are highly correlated with each other. And in other words, you can say that one variable becomes redundant. That means you can replace that or you can remove that variable. And then you can use only one predictor variable out of those two correlated ones. So let's understand this concept with few examples. So like here, if I am predicting cholesterol, and if I take weight and BMI both as a predictor variable, in that case, it is bound to cause a multicollinearity. In this case, you can see, this is the cholesterol level, if I take like blood pressure, exercise, and weight and BMI. So we know that this BMI is derived from weight only. So we should not take both these variables. So there will be multicollinearity between weight and BMI. Again, if we have to predict the lung capacity. So in this multicollinearity, I want to predict the lung capacity based on some physiological factors like age, height, arm length, and weight. So you can see here that the height and arm length, this will be correlated with each other, because we expect that a person who is having a more greater height will have a more arm length. So that's why these two will be the multicollinearity. So now don't confuse autocorrelation with multicollinearity. Multicollinearity is between the two variables, whereas autocorrelation is inside single variable. That's why its name is autocorrelation. And this multicollinearity, so how do we diagnose this multicollinearity? So there are two statistics which this Jamovi produces, which is the tolerance and VIF. And we will see this. Okay, there's one more example before I switch to those two values. So again, if you are predicting a heart rate, and if you take age and resting heart rate, then this resting heart rate and age might be correlated or collinear. So these are few examples. So how do you check for multicollinearity? So this basically, there is a correlation matrix. You can inspect the correlation coefficient. And if the value of correlation coefficient is more than 0.8, many textbooks says that more than 0.9, but we generally keep it more than 0.8, then those two variables are showing multicollinearity. Again, since you have to do this separately, the Jamovi produces a statistics, which is the VIF and tolerance. So VIF is the variance inflation factor, and the value of VIF should be less than 10. And tolerance is the opposite of VIF. So the value of tolerance should be more than 0.1. 1 by VIF is the tolerance. So VIF is simply the reciprocal of tolerance, 1 by tolerance. So if the tolerance value is less than 0.1, so VIF should be more than 10. That's the multicollinearity. So any variable showing the VIF more than 10, you can try removing that variable. Then that outlier, you can do the box plot of residuals, because in Jamovi, you don't have a way. In SPSS, yes, there are many ways to check for outlier. In Jamovi, you can do that. Like you can go with this plotting the box plot of residual that we will show you. And then you can check for the influential point, which is the Cook's distance, which I will be demonstrating now. And this we have seen, this is the homo versus heteroskedasticity, which we were discussing yesterday. In this case, you can see these patterns. And if your data set is showing a pattern like this, then it is the heteroskedasticity. Now, before I move to the, okay, so I think should I first tell them linear regression and then this? Books. No. I will finish with this presentation and then I'll go to the demonstration. So these are the few articles, how to report the multiple regression table, what all to report. So this was one article, which was the determinants of quality of life. So in this case, the dependent variable was quality of life during induction therapy in pediatric acute lymphoblastic leukemia. So you can see here that the author has measured the quality of life and he has used the child health questionnaire, which is the CHQ, and the PIDS quality of life cancer version questionnaire. And then he has performed a multiple regression model. So these child health questionnaires were having these many components like physical functioning, role limitations, bodily pain, behavior, mental health, etc. And you can see how he has presented his result. So he has written the determinant. In the first column, he has written the various scale and then determinants, its p-value, the beta and standard error, and then R square. Now, can you tell me how many multiple regression analysis are there in this table? Yes, I'm expecting any few answers in the chat box. 4. Perfect. So what he has he has incorporated all in one table, because whenever you submit your manuscript, there's a limitation of the number of tables. Generally, it should not be more than 5, 6, or 7. So that's why what he did, he has combined all the 4 together, but it's the 4 separate regression. So like role limitation, he has taken these 2 determinants like female parent and child age, bodily pain like these 4, 5, then parent impact time like these 3, and then psychosocial summary these. Now my next question is, how many outcome variable and how many predictor variable are there in this table? So since you have already said 4, and how many predictor variable? Yes, can you please tell me the number? 13. So if you see, there are some repetition, like child age here also, this here also, female child. So you can see like parent female, child age, this day since diagnosis, this 4. And then again, treatment toxicity 5, university education 6. This is again repetition. This is repetition. So this is all repetition. So I think 6, 7, something like that. Yes, Poonam is writing 6, yes. So can we make a model equation from the value given here? Can we make a model equation? Yes or no? So the value of constant is not given here. So we cannot make an equation. We can only write the coefficient. We can say that, but we cannot make a equation. Now this is another article, evaluation of a health literacy level of hypertension patient. Referred to specialized clinic of this cardiovascular hospital and its correlation with hypertension control. So here, after that period, Pearson's correlation coefficient, we have not taken the overall SNP. We have just taken the relevant portion. The linear regression was used to examine the relationship between the health literacy and hypertension control. And he has presented the result like this. So you can see again, it is the multiple linear regression These are the regression coefficient, and this is the standard error and the significance level. This is again one way. Another article, factor associated with the delayed diagnosis of breast cancer in the northeast Thailand. So he has taken factor like affecting the doctor delay by identifying the linear regression, and then second by then he did some more dichotomizing the data, and probably he has applied the logistic. So here you can say the patient delay is the dependent variable, and the independent were like family income, previous breast cancer, and smoking. And then again you can see here multivariate and one and multivariate and univariate. So this is the doctor delay in breast cancer. You can see these were the factor. And in univariate means it is basically the univariable. That means the simple linear regression, only one variable. And here he has taken the multivariable, all the factors. So you can see here he has made two model, A and B. In model A, he has taken distance from the hospital. That's why you will see that here you can see this value, but here this value is absent. You cannot see anything here. Similarly, you cannot see anything here. So if you have to present result in the single table, yes, all categorical variable here. I was also seeing the same thing, all categorical variable. Maybe, yes, that we can try that also, but ideally in that case, the dependent, that's why he has written that later he has dichotomized it. And then pregnancy outcome variable and associated factor. This was again, although he has written this BW is the birth weight, HC is the head circumference, CHL is the crown heel length, and PW is the placental weight. So you can see that he has written like model 1, 2, 3, and 4, but this is not model 1, 2, 3, and 4, because he has taken different dependent variable in all these four models. Generally, we write model 1, 2, 3, 4 when the dependent variable is same, but he has used this terminology. And then this is one more article which is citing the gender differences in the psychosocial predictors of attitude towards reporting child sexual abuse. So he has measured the attitude score, and you will see that the dependent variable was the attitude towards the reporting child sexual abuse, and he has done it separately for males and females. So age, family cohesion, social support, and interpersonal manipulation, callous effect, these he has taken. Then again, this was one article, and this again he has done like univariable and multivariable. Here he has reported beta 95% confidence interval and p-value. So you can say that it is up to you. Generally, you should report like standard error also, and that F also. I think I'll show you. Yes, this you can say here that this person has reported both the F statistics, square, and here you can say these are the two model. We will do it like this today. That in one model he has taken smoking and PM10. This article was like the effect of air pollution on mortality and clinico-pathological features of esophageal cancer. So he has taken initially the two variable, that is the smoking and PM10. And later in the model 2, he has added one more variable, that is the SO2. And then he is showing the R square. So in first case, you will see the R square is 62%. And then with the addition of this SO2, the R square has become 67%. And both these were significant, like this also and this. And this is the value of ANOVA or the F statistics. So this was, this is the way, there are a lot of flexibility in reporting the result. Now coming to your Cook's distance. So this is one data which we have created just to show you the Cook's distance. So here you will see that I am now using the multiple regression. Okay, Damini is asking what is the ideal table. Yes, we always encourage to report both univariate and univariable and multivariable. Actually, you will find these terms, many people, they write variate. And many people, they write variable. But since you have written here Tanvi, that's why we want to clarify it. Variate term we use when the dependent variable is 1 and multivariate when the dependent variable is more than 1. But this term, you will see it being used very loosely in the literature. So rather, we will advise you to write univariable and multivariable, because this, in context of linear regression, there is only single dependent variable. But the number of independent variable, if it is 1, it is univariable. If it is more than 1, it is multivariable. Okay. So that we advise, because that's the correct way. We have seen a lot of literature and we came through on this conclusion that we should use the variable term instead of variate. That is one thing. Second is, yes, we will encourage you to write both these univariable and multivariable, because that shows the effect of the independent and then all together. But if you are going with the model making, that a model builder one, which we will see now, in that case, you can skip this univariable, because then you are adding variables stepwise. So then in that case, you may skip that also, and you can only show the model 1, model 2, model 3, and model 4 details. And then you can write ultimately that you have accepted model 2 or model 3. We will see, depending on the R square. And what is the decision to accept which model? That is also a very important concept to remember. We'll discuss that. So, is it clear, Damini and Tanveer? Ideal table is, we would rather say you include like standard error all, what Jamovi gives. That should be there. There's no problem writing those values, because ultimately you are not going to explain each and everything. But giving that helps the reader to understand like standard error, and that your T value and F value, R square, that should be there. Coming to the Cook's distance. So here my dependent variable is cholesterol, and I am taking like age, weight, and exercise R. All three as a dependent variable. So this is my multiple linear regression. So you will see that R is 0.4 and SBP also. These are my 4 predictor variable. I'm not taking stress right now, stress level I mean, not stress. So I'm not taking stress level as a predictor variable. So you will see here that the R square is 54%, means all these 4 variables together, they express the variance in the cholesterol level. Now, if you see the Cook's distance, can you see the Cook's distance? How much is the Cook's distance? It is 1.68. So is it acceptable? What should be the Cook's distance? What should be the value of Cook's distance? Yes, it should be less than 1. Agree. So now if my value is this, then what will I do? I'll go, because then I'll have to see the individual variable. Which variable is giving this high value? So then you have to go to this save option and click this Cook's distance, and then come to the data. So then you will see that there is a new variable which has appeared here. So this, we have shown it only with 20 data. Can you see? So if you see it individually, which is the variable where the distance of this Cook's distance is more than 1? Which is the serial number? Yes, can you all see and tell me? 16 and 30. So which is the 16? Let me check. Okay, 16 is 1 point. Yeah, okay. 1.01 serial number, 16 and 20. Agree? So it's always good that you first remove those values which has got the highest one. Okay, good. So now what I will do, I will go and then what to do now? I will have to remove this. And now with this Cook's value, if you see what is happening to this. So right now my age is not significant. My weight is also not significant. The only significant variable in this regression analysis is the exercise R. Can you see this? All four other are not significant. They are not predicting significantly. So I'll go to this filter and I'll hide this 20 first. And then let's see. So how we have applied yesterday? Can anyone tell me what command I applied yesterday?
Row.
Yes, very right. So I'll go to row. Let me see. Log 10, this minimum. Okay. No, by typing it is not coming. No? I'll have to see. I will explore. Variance then not contain hook match. Yes, row. So I've double clicked this. Then I will apply this exclamation mark equal to, and then I will select 20. So now this is there. And if you see the value of Cook's distance now, this has become 0.1. Can you see? It is 0.1. So now your like this has, and your R square has also improved. Initially it was like in 50s and right now it is 62%. And you can see that the regression coefficient has also changed. I can show you with one and let me hide the other one, 16. So I may again go to filter and I will add another filter. No, but then both of these, okay. And then I can copy paste that. And here I may write 16. Then you can see 16 is also not there. So now you can see the weight has become significant. Initially the weight was not significant, but now the weight is significant. And R square is now increased to 89%. Can you see here? R square is basically, here you can see, it is 89%. And this weight, which was initially, it was not significant, only the number of hours of exercise was significant, that has become significant. And this distance is also, now it is less than 1. Yes. So is it clear to all of you how this Cook's distance? So what is the step? Go to this overall Cook's distance. If it is more than 1, then you click the individual Cook's distance in the data set. And then you apply the filter. So right now you see it is 89%. And if I again go and hide these filter, then what will happen? You can see I will make these this filter inactive. And then you can see it is 54%. So your accuracy of model and even the p-value. And we did not focus on this estimate, but let's see, this is the estimate. So what I will do, I will copy this and I will paste this in a Word document. Okay, here. Just to compare. And then you can see. So this is one result. And if you go to Jamovie, again, make this filter active. And then if you see this, I will again copy and I will paste it here. I will move this little up so that we can compare. So now can you see? Here the coefficient is also different. For weight, it is 0. It is now 2.92. Here the exercise are, it is 23. And here you can see it is 13. And the p-value also got changed. 0.01 say itna, and that weight has become significant. Here the weight was not significant. It was 0.985. And here it is significant. So can you now, is it clear to you how the, removing these Cook's distance? And yesterday we discussed that there were three things: outlier, the other was the leverage point. So outlier and leverage is not that important because they are also important. But the Cook's value that shifts the, slope. So that because Cook's distance has got both these two values together. So both high leverage value and the outlier together makes a high influential point, which we measure using Cook's distance. Okay. If it is clear to you, then we will go to another demonstration that is on the homo and heteroskedasticity. And then I will show you the standard multiple linear regression. So yes, I can see few yes. So I will move ahead. And then we'll go to so this was the data of heteroskedasticity. So again, if I click this, you can see this is the graph. I am predicting systolic blood pressure based on the stress level and age. So you can see any pattern here. Can you see the pattern of these residuals? Like funneling, and then again, here also you can see the individual one. So this is like the distance is increasing as you move across the stress level. So that's the heteroskedasticity. So if the assumption of homoskedasticity is not met, then what to do? What is the option? Which type of regression you should apply? That is the weighted least square regression. Can you see an option here? Weights. So you have to apply weights here. I am not telling you right now. Once we are done with multiple linear, then I will come to this option. Otherwise, I don't know how everyone will take this. So I will go first to the this demonstration of multiple linear regression. So if I see the question, the data set is same. So I have to use appropriate regression approach for predicting cholesterol level, and there are 4 predictor variable. Initially, I took only BMI, but now I have added age, gender, and systolic blood pressure. 3 more. So now there are 2 ways to attempt this. So I'll open this data. Now I will come to this. So my dependent variable here is the cholesterol, and my independent variable is the BMI, and then systolic age, systolic blood pressure, and then gender. So gender I have to move here in this window. That is the categorical one, which is the factor. So I can see the overall R square here. It is the 0.20. Now, if I want to take these one by one, so this was all together, and this is the enter method. So there are many ways of doing it. Like in SPSS, you have got options like enter, forward, backward. But here in Jamovi, you will see it gives you stepwise or hierarchical. So what I would, because in this case, I do not like it is, I am not getting like which variable is contributing the most. So in that case, what I can do, I can try. So I will put all these, maybe one variable only here, and then I will come the initial one, because initial I took BMI. So we have done this BMI, which was predicting the 18%. And this gender, you may take this. So I will move this back here. Now I will show you the model builder. So in block 1, that is my first model, I have only used BMI, right? Now I have to add a new block. In the second step, I will add age. So how I will do? Since I have not entered age here, it will not show. So I will have to enter everything here. Then only this option will be available here. So now I have entered BMI. Now, okay, this is now I can click that and I will add a new block. Then I will add age here. And just focus on this blue line. I also get confused many times. If this blue vertical line tells you that this block is active. So I will move this here in this age. So then your model 2 will be created. And then keep on seeing the right hand side. So initially it will give you the result like model 1. The R square is 17%. And model 2, there was a change in R square. And this change in R square was 0.01. Can you see this? So there was only change of 0.1%, like 1%. 0.01, that was change in 1% with model, with adding this age as a predictor variable. Okay. And then you can see like with this model 2, this is significant. BMI, it was significant previously also. And your age is not significant. It is 0.06. Now I want to add one more variable, that is the SPP. So for that, I will add one more block and I will add this systolic blood pressure in the third block. So then you can see that this is the model 3. And here with this drop down menu, you can see it will give you the result of both model 1, model 2 and model 3. So now there is no change in R square value. That's why this is 0, 0. If you see the R square value here, it is 18 and 18. There was no change. And here also in the first model, there was a change of 0.01, but in the second there was no change. And now if you put another, that is the gender here. Okay, by mistake I have entered in the same block. So what I'll do, I'll add a new block and I'll add gender to the new block. And then you will have a model 4 and you can see the R square. So now with the addition of gender, the R square is 20%. And there was a change in 0.01, that is 1%. So then again, you can say that there is not of much difference. It has only changed from, yes, that can also be done, Poonam. That can also be done. You can add like, you may enter here in the block 3. So gender I may put in block 3. So that way this fourth model will not be there. In third block, you have entered 2 variables together. So like in this case, you will see that these 2 appear together, and then that because that 0, 1 you have entered it together. So there was in model 3, you can see that there was a change of 2%. So that can also be done. So this was regarding the model specific result. And then coming to the reference level, it will show you in this case, the reference is the female. So you can interpret this estimate that if female is the reference, then in male, the value will always be minus 13 less as compared to the female, because it is sign is minus. So cholesterol level, and again you have to keep the other constant. So how will I interpret it? The male were having 13 unit of cholesterol lesser than the female, keeping all other variable constant like BMI, age and SPP. Similarly, SBP, you can write that with 1 unit increase in the systolic blood pressure, the cholesterol level decreases by this 0.12. And similarly, the age and BMI we have discussed. So significance, you can see it is only the BMI which is a significant. So you can write that addition of new variable is not, increasing the predictive ability. The R square change is only from 17% to 18%. It is not much of the change. And that's why we say that if you are adding multiple variable and it is not yielding any extra like R square change, then you should keep it simple and then you can go with only 1 or 2 variable. Right. So this is the way we make, and then now I have not checked for the assumptions. So the assumption checking would be done in this case also. In this case, I will check for collinearity, because we have discussed this collinearity, and then you can see that BMI, age, SBP, and gender. So now can you tell me any variable which are showing collinearity? Yes? No. Okay. And then you can check others also. BMI age, the value of VIF should be less than 10. Sorry, more than 10. So you can see all the VIF is less than 10. And the value of tolerance should be more than 0.1, which is there in this case. Normality test, I will not go because it will tell me the Shapiro-Wilk. And then residual plot and Cook's distance you can check. So the Cook's distance in this case is it is 0.01. So that assumption is met. Multicollinearity assumption is met. Autocorrelation you can check. This is QQ plot showing the normality of the residual, and this is the residual plot. So you can say there is no pattern. So we can say that the this is homoscedasticity, that concept is met, homoscedasticity. And then you can see the Durbin-Watson statistics, that is the autocorrelation. So it is only 0.03, that means it is less than 2. So that's why. So gender being categorical also have collinearity. Yes, it applies like biserial correlation. It is, that's why I said collinearity will also there with the categorical also. They are correlated, means it may not be the Pearson's correlation, but some other statistics, but it is also there. Their categorical variable will also be there as a collinear variable, might be there. So that's why it is there for the gender also. Any other, then again, we will go to this model fit. In model fit, we'll go with this F test, adjusted R square, sorry. And then model coefficient, you want ANOVA, and then estimate 95%. And you can see the table. So this is the intercept, standard error. This is the lower and upper 95% confidence interval of the intercept. I have not clicked the standardized intercept, but you can do that. You can click it, and its confidence interval also. So that standardized beta that will appear here. along with its 95% of confidence interval. And then that's it. In save, I don't want to save anything, but you can save yes. So Poonam was asking yesterday, like how to predict, how does this predicted value is there? So maybe you can write, first you can write an equation here and then we will see. So what will be the equation here with this? All of you please write. It will be 113. So it will be 113 plus 4.98 into BMI plus 0.36 into age minus 0.12 into SBP. And in case of male and female gender, you can keep like for female, it will be no value. And if it is a gender is a male, then it will be minus 13. So now if you have to write a predicted one. So let's, for example, I will remove one variable so that it becomes simple. So let me remove this age and SBP. Let's keep it simple, only BMI and gender. So I'll remove this also. So this is the 134. Let me write it. So 134 plus, and then you can write 4.5. And then you can multiply it with the BMI multiplied by BMI and depending on the gender. So I am making this equation for a male. So then you can like minus 14.75. So I am clicking this option of predicted value and then we'll calculate predicted value. So let's say I have clicked this predicted value and then I'll go to the data. So now let's calculate, let's see for gender. So let's calculate it for this person. 83, this male, serial number 1. Male with a BMI of 25.5. What will be the cholesterol, value of cholesterol? All of you please calculate. Okay. Yes, you can see the equation and you can calculate it. Yes, I think equation, I'll have to put it again. Okay, all that has gone. So I'll move this back. And here in the model also, only 2. So now let's say this is the one equation. Now all of you have written that 134.84 plus 4.5 into BMI. And for male, it is minus 14.75. Now what will be the predicted value for serial number 1 patient? Whose age is, so age is not there, who's a male and BMI is 25.5. All of you please calculate. And let me see the chat box. Two 235. And let's see the predicted value. So this is the one. 234.9. Can you see this value? Yes. So like, so now do you know how this predicted value comes? So this is based what Dr. Poonam asked yesterday, like how this predicted. So this predicted is based on the equation. Okay, yes, female you can also take where you will not add this. So let's say, let me see. You can take this fifth number female, 27.43. 27.43. So all of you please do it. So it will be like the above. You can just do the, okay, no, but that BMI is 27. So you will have to do that again. So this is 258.27. So I'll go and see this. See this one, Dr. Poonam, 258 point. This one. Yes. So now have you understood? So you can check, you can do that in your own data set and you can check using the equation. So basically in categorical, what happens? The reference category, you will take that as a 0 because there is no addition. But the other category, like here, you have to predict in male. So male will always be 14.75 unit lower than the female. And that value will be added or I mean deducted. So I have to repeat how to do for males. Okay. So like you can see in the chat box also, but let me explain. So male, can you see that this is a reference value? So this is the reference value of male. So for male, my equation will be like 134.84. So I'll open this calculator. And I'll show you with the this first male. Okay, Dr. Shamshad is saying to take some other. So I'll take the second one. So age is 70. Sorry, not age. Male is this thing and BMI is 26.63. 26.6. So my constant is 134.84. And then I have to multiply this with 4.5 into. So how I'll do it? So 134. So let me first do the calculation of that 4.5. So 4.5 into this BMI is 26.6. 26.6. This is 119.7. And now I will add this to the constant, which is 134.84. So now I will add this 134.84. So this equals 254.54. But here you can say that in males, this value will be minus 14 unit less. So that's why for male, I have to minus 14.75. That this equals to 239.79. And that's the value 239.79. I can see the next second number. This was the one, 239.89 or 79. So, yes, Priyanka is asking, can we use categorical versus as predictive variable in multiple regression? Yes, you can use the categorical variable also as a predictor variable. But generally, I'm not sure only categorical variable can be used as a predictor. That can also, because that we have seen it. We have seen it, that we can use it. Only categorical as a predictor in the multiple regression. In that case, like only based on reference level, you will calculate the value of the dependent variable. So if you are clear up till this point, then I think anything more to show it to them? Heteroscedasticity, I have shown it. Okay. So now we'll go to the breakout room and we'll practice on this multiple linear regression. So Dr. Naveen?
Ma'am, 1 minute, ma'am. Ma'am, can you repeat that part, ma'am, predicted? How we will calculate for the other reference group, like for male? Now, just you taught now, last 5 minutes.
Okay. So like, so for categories, we always take the reference. So I'll write you the equation. So equation will be 134.84 plus 4.5 in the bracket. It will be the value of BMI. And then in minus, I'll do one thing to make it more, 14.75. And then in the bracket, it will be the code of gender. Means, so like reference, we always take as 0. So if female is 0, then this whole will become 0. And then male we take as 1. So if you multiply this by 1, then all the male will have a 14.75 value lesser. And then you can have this. If you like change the reference level, then it will be the other one. See, if I change the reference level here, male, then this minus 14.75, it will become plus 14.75. Now that again equation is gone. So, so this 14.75 will be plus. So that's why, since it was there as a female, then that will be the equation. And you have to, for male, you have to reduce this, deduct this minus 14.75 in the overall value. So reference level, because it is 0, we take this at 0 because we say that in comparison to the female, the male has got 14.75 millimole of cholesterol lower. So that's why it will be like minus 14.75. Is it clear, Naveen? Or should I repeat it once again?
Ma'am, not this one, ma'am. The predicted. Like in save, we will click for the predictor value, now, ma'am. Just now, like
Okay.
we have to deduct it from.
Okay, data you want to say?
The last column created, na, ma'am, predicted 239.89. How it came? You explained on
Okay.
calculation now, na, ma'am.
Okay. So it was
Yeah,
on
that one I know.
So there is an option known as the save here. So I've clicked this predicted value. You want to ask this?
Yeah, yes, ma'am. How it came? Just you explain, na, ma'am, by a calculator.
Okay. So that was using the equation because I have
Yes,
not.
ma'am.
Okay. So that was based on the individual data. Like I took, this was the second case.
It will keep changing.
So this was calculated, this predictor value was calculated for a male, this second number. I have not taken age, but for a male whose BMI is 26.63. So if you replace this value in that equation, which I have created here, then you will find this value. That's why I have like.
Okay, ma'am, got it, ma'am. It also based on the equation only.
Yeah.
Okay,
Because
ma'am.
Dr. Poonam
Okay,
asked this question yesterday, that how to how this predicted value came here. So that's why I wanted all of you to realize
ma'am.
this, that if you take all these variables and put that into that equation, you can get that predicted value, which The software also gives you if you click that predicted one. You just have to match just
Got
as
it,
a
ma'am.
part
Got
of
it.
learning,
It's just a bad. You explain now. Okay, ma'am.
just for learning, like how it
Okay,
came
ma'am.
in the background, how the software is calculating the predicted value.
Got it, ma'am. Got it, ma'am.
Okay. And Dr. Paramita, dummy coding we are not discussing because it will complicate the matter. In the literature, you will see that people have used dummy coding, but we have tested in Jamovi. In the background, it is doing the dummy coding. So you don't have to do the dummy coding. And we have done the data analysis doing the dummy coding and without the dummy coding. And the results are same. So dummy coding is we will tell you once this practice session gets over, we'll tell you the concept of dummy coding. There is a data set and we